Hello everyone, my name is A. Harshavardhan, and my team members are D. Vivek Kumar, P. Rajesh Yadav, and G. Sasi Kiran. We are final year mechanical engineering students from NBKR Institute of Science and Technology. Our project is titled Fabrication and Analysis of Wire Arc Additive Manufactured Radial Flow Impeller Using Copper-Coated Steel. Our project guide for this endeavor is Dr. P. Srihari Reddy sir, who has been guiding us throughout the project. Now, let us introduce the core technology used in our project, wire arc additive manufacturing. Wire arc additive manufacturing, commonly known as WAM, is an advanced metal 3D printing technique that falls under the category of direct energy deposition processes. In WAM, a metal wire is continuously fed into an electric arc, which acts as the heat source, melting the wire and depositing it layer by layer to build the desired geometry. This process is typically carried out using welding technologies such as MIG, TIG, or plasma arc, and is controlled by robotic arms. Due to its efficiency and flexibility, WAM is widely used in industries like aerospace, marine, and tooling, where custom or large metal parts are required. This makes WAM a powerful solution for modern manufacturing challenges. To carry out our project, we followed a structured methodology combining CAD modeling, simulation, and fabrication. This is the CAD model of the radial flow impeller, created in CATIA V5 using the finalized dimensions. The design includes a 144 mm base diameter, 25 mm shaft, 41 mm inner and 44 mm outer blade diameters, 9 mm base thickness, and 25 mm blade height. This model was used for simulation and fabrication in the next phases. Using KUKA Sim 4.3 software, we created a complete welding path for the radial flow impeller by programming individual parts for the base, hub, and blades. 3 welding loops were programmed to build the impeller base. The first loop used circ commands to create smooth circular arcs, with 1.5 mm side-to-side spacing and a 3 mm incrementation for every layer. The second and third loops followed a zigzag pattern, alternating arc start points to create a back-and-forth path that helped reduce heat distortion and ensure uniform deposition. For the hub, we used nested loops, vertical steps controlled by the outer loop, and circular weld passes by the inner loop. Blade 1 used a spline path for smooth, continuous welding from XP38 to XP64, with same arc-on arc-off points of every layer. Blades 2, 3, and 4 followed a zigzag pattern using PTP, LIN, and circ commands, with alternating arc start points for better heat distribution. Each layer stepped up by 3 mm, ensuring consistent and controlled vertical buildup. After verifying the toolpaths, we exported the KRL code into USB and loaded it into the robot via USB. Using the KUKA Teach pendant, we ran the program to begin fabrication. To carry out the wire arc additive manufacturing process, we set up our experiment using a precise and fully automated robotic welding system. The main equipment used is the KUKA robot, specifically the KR6R1440-2 Arc HWE model, a lightweight, high-speed robotic arm designed especially for precision arc welding applications. This robot is controlled by the advanced KRC5 controller, which handles all motion commands and synchronization. For the welding process, we used the Fronius TPS320i, a smart and efficient welding power source, perfect for our application. We used the cold metal transfer, or CMT, technique. This method allows for low spatter, low heat, and highly controlled metal deposition, which is ideal for 3D printing metal parts. In the WAM process, we used controlled welding parameters that are 140 amps current, 14.2 volts, and a 3.7 meters per minute wire feed, for smooth deposition and minimal spatter. The filler material used was copper-coated steel wire, specifically ER70S6. Chosen for its excellent arc stability, low spatter levels, and suitability for high deposition processes like WAM. This live video shows the fabrication of a radial flow impeller using wire arc additive manufacturing. The KUKA robot builds the part layer by layer, starting from the base, then the hub, and finally the blades, following the programmed path with high precision. This is the final stage of fabrication, where the radial flow impeller is fully built using WAM. The layers are complete, and the part matches our simulated design with some minimal dimensional changes. After completing the fabrication of the impeller, we conducted a comprehensive finite element analysis using Alter-Inspire Print 3D to assess the part's strength and reliability. The analysis revealed a maximum stress of 400 MPa near the curved blades and a displacement of 0.273 mm, both well within safe operational limits. Additionally, we validated the weld bead dimensions using Simufact Welding 2024 software. The simulation results closely aligned with our physical tests, with a bead width of 3 mm, confirming the accuracy and effectiveness of our welding setup. Before we delve into our project journey, we extend our sincere gratitude to Dr. P. Srihari Reddy Sir, Professor in the Department of Mechanical Engineering at NBKR Institute of Science and Technology, for his valuable guidance and unwavering support throughout our project. His expertise and mentorship were instrumental in our success. Thank you for watching.